Hi folks, welcome to section 1.5. We're going to talk in this section about continuity, or the idea of a continuous function. So I want to remind you of something that you might have noticed, but maybe not explicitly as we've been working through our chapter about limits. In some functions, the limit and the function value are the same number. So in this first graph, for example, if I calculated the limit as x approaches 3, it looks like that y value's about 4. And if I calculated f of 3, it would also be 4. But then in the second graph, they'd be different. The limit as x approaches 3, f of x, that's what's happening down here near 3. So that looks like it's about 4 again. It's just a little bit below 5. But the function value is something above 5. It looks like if I'm estimating that down here, f of 3 is about 6. And so you might notice that the first graph, looks more like the kinds of functions you're used to working with before. It's kind of nice and does what you expect it to do. But the second one is strange. It has this random hole in the graph and then this point just floating up in the air. And so we want to talk about kind of how those functions are different and how can we tell that other than just from looking at a graph. So the ones where the limit and the function value are the same, they're the nicest in a lot of ways. They're the ones you're used to seeing, but they also have some really nice properties. But other functions that sometimes come up in life have these jumps or breaks that make things a little bit complicated. Quick example of that. Suppose you start a new job and the deal is first 30 days you're making minimum wage. It's the trial period. All right, well, after 30 days, you make $8 per hour for the rest of the year. And then after that, your rate goes up by $1 per hour every year. Now, so minimum wage is like $7.25 now, I think. So if I was going to draw a graph of this, then one thing happens up to 30 days. And then something else happens up to 1 year. I know my graph is not to scale, but I just want to show you what's going on here. So for the first 30 days, we're making minimum wage. And then it's not like you go slowly from minimum wage up to $8. It's one day you were making minimum wage, and the next day you've jumped up and you're making $8. And you make $8 an hour for the first year. And then again, it's not like you go slowly from $8 an hour up to $9 an hour. At the end of your first year, one day you're making $8. The next day you're making $9. So this function has these sort of built-in jumps. And no matter what your hourly rate is, when it changes, it's going to jump. So we want to be able to compare this to a function that's continuous and see how the properties of the function are different and what's different about them. So by the time we get to the end of the section, you'll be able to talk about how you can use a limit to decide if a function is continuous on a graph, also from an equation. You'll be able to explain where a function is continuous and where it's not. We're going to talk about something called the intermediate value theorem, and you'll be able to determine if it applies to a particular function and then use it to predict something about a function. So this first video, we're just going to talk about the idea of being continuous at a point. One single point at a time. Later, we'll get to intervals. That'll be the second video. So a lot of people meet the idea of a continuous function as something that you can draw without picking up your pencil, or something that doesn't have any jumps or holes or breaks in it. And that's a pretty good definition to keep in your head. It misses some subtleties, but as a starting point, it's pretty good. So I want to look at these 3 graphs we've got here. Think about which ones are continuous based on this sort of loose idea of drawing a graph without picking up your pencil, and which ones are not. So this first one, I can follow that whole graph without picking up my pencil, so I think that this one should be continuous. I'm just going to put a C to keep things nice. If I move over here and I'm trying to draw this graph without picking up my pencil, I have to pick up my pencil to get from one point to the other. So this one is definitely not continuous. Let's go to the third one. I'm following the graph. But I have to pick up my pencil to make this dot up here. So that's not continuous. And then this last one is maybe the trickiest. I follow my graph, but the problem is that I can't get across that hole in my graph unless I pick up my pencil. So this one is really, really the hardest one. Sometimes people want to say, well, I could draw it by doing some kind of like this business. But if you're thinking about it as a graph, like that's a hole. You have to get across it, and if you're going to stay on the graph, then you have to pick up your pencil and kind of jump across it. So this one's not continuous. So I only got one of these that's continuous. Well, what can we say about their limits versus their function values? Let's take a little bit of a more careful look at that. So same set of graphs. If this one is F and this one is G, this one's H, and this one's K. So for F, that's one of the ones where in all of them I'm looking at x approaches 3. I know K kind of ran off the end here, but I think you can see enough of it to be okay. Well, this is exactly the one we started off with. The limit and the function value are both 4. They're both this one single solid point. But for G, I'm saying the limit doesn't exist, and it's because I've got one point down here on one side, but my y values are going towards this open circle on the other side, so when I have 2 different y values headed to 2 different things, that's when we get a does not exist. But if I just look at the function value says go find the solid dot. So here it is. And it looks like that's 4. So G of 3 is 4. So there's a different. One doesn't exist, one's 4. For H, my limit is at this open circle. It looks like that's about 4. But my function value, the solid point, is up here a little bit bigger. We're going to estimate that it's about 5. For K, last one, it looks like the limit, there's a typo in that, sorry. It looks like the limit for K should also be 4. It's up here. But this time the function value, K of 3, doesn't exist because there's no solid dot anywhere. So the thing that you should notice is that, remember, F was the only one that looked continuous. It's also the only one where the limit number and the function number are exactly the same. In all the other cases, something's different. One doesn't exist and the other does, or they're just flat out different numbers like with H. So it turns out that we're going to be able to define what it means to be continuous in terms of limits and function values. All right. So a function gets to be continuous at a point. Here's how you check and find out if the limit at that point is the same number as the function value. And then if you have a place where, sorry y'all, if we have a place where the function is not continuous, we call it a discontinuity. So it seems like that should be easy enough. You're just testing to see if the limit value equals the function value, and then that helps you know whether or not it's continuous. If they're equal, then it is, and if they're not, then it's not. Well, really, though, we're checking three things here. Because remember that limits and function values, well, they aren't quite so simple as to just always be numbers. Okay? So really, there's three things that have to happen. The first one is that f of c, that function value, it has to be defined. Like, it has to be a number that you can tell me what it is. Unlike this guy right here, where our function value at 3 didn't exist. So that would be bad. So function value has to be defined. The limit has to exist. And one way to think about that is it's a single number. Okay. And finally, if both of those things work, f of c is defined and the limit exists, then we check, are they equal? Because if one's existing and one's not, then they're not equal. But we want to be sure we don't lose track of that. So the way it works is, think of this like a checklist. If any one of them fails, if any one of them is not true, then the function's discontinuous. It's not continuous. And we'll get into the intervals in just a little while. Hang on, back up a second. If any one of them fails, it's discontinuous. If all of them check, if you can check off all three of these, then the function's continuous. And then in the next video, we'll talk a little bit more in detail about this, but it gets to be continuous on an interval, say from like 1 to 5 or something like that, if the function's continuous at all the points inside the interval. That's just all there is to that. So let's look at a graph. And on this one, we're going to decide where the graph is not continuous. And we're going to answer, every time in this class we see a where question, we're going to answer it with x values. So places where it's not continuous. Well, let's see. So I can follow my graph up until I get to -2. And at -2, I have to pick my pencil up. So it's not continuous at -2. And I keep following my graph, and I have another hole at -1. Have to pick my pencil up again. It's not continuous at -1. Keep following my graph. Now, 0 has this like funny change of direction, but I don't have to pick my pencil up to make that, so that's okay. The next time I pick my pencil up is right here when x equals 2. And then for the rest of the graph, it just goes and I don't have to pick my pencil up. So I've got 3 points where my graph is not continuous. And if I wanted to, let's say, for example, at 2, I could support that by saying x is not continuous Sorry, x. That the first one should say f. The function f is not continuous at x equals 2 because the limit as x approaches 2, f of x doesn't exist. And that would be enough. As soon as the limit doesn't exist, then we've got one thing on our checklist. Remember our checklist back here? I can't check this one off. So as soon as that's the case, then I can go ahead and say it's not continuous. But also the function value f of 2 is -4. Alright, so that one's got 3 points where it's not continuous. What about if I don't give you a graph? What about if I give you some equations? So we're going to do a couple of examples. I want to point out that 1 and 2 are exactly the same functions here. They just have different x values, and they might have different answers. So it's not entirely only about the function. It's also got something to do with the x value. And then the third one we're going to do is a piecewise function. So I'm going to put those up one at a time so it's a little easier to see. So let's decide if this guy is continuous at x equals -3. So back to our checklist. The first thing in our checklist was that f of -3 should be defined. In other words, it should exist. So let's see what happens when we try to calculate f of -3. So I do 5 times -3 squared, 14 times -3 minus 3 over, not an x, that should be a -3. -3 plus 3. Ooh, I'm already seeing a problem. I've got a 0 over here in my denominator, and that's gonna not do very good in terms of existing. In the numerator, you should come up with a 0. Ooh, I got 0 over 0. So in this case, I can't even check off the first thing on my list. I cannot plug -3 into this function and get a number for the answer, because I get the 0 over 0 thing. And so as soon as I run into one thing on my checklist that I cannot check off, I can stop and say, no, this is not continuous. All right, what about at a different point? So same function, different point. So let's see if f of 0 is defined. Well, so we have to plug in 0, so that'd be 5 times 0 squared plus 14 times 0 minus 3. 0 plus 3. Oh, sorry, y'all, that's a 3. -3 over 3. Well, that's just f of 0 is going to give me a -1. So that's defined. All right, so far so good. Next thing we need to check is the limit. The limit as x approaches 0. 5x squared plus 14x minus 3 over x plus 3. Well, so the first thing we always try is plugging 0 in. Well, wait a minute, that's what we just did. So, alright, so we just did that, plugging 0 in, and we got -1. So far we're doing pretty good. The limit exists, the function value exists. The third thing we need to check is, does the limit of our function equal f of 0? Did 1 and 2 have the same answer? And sure they did. They both had -1. And so we say this one, because we checked all 3 parts of our checklist, it is continuous at x equals 0. So it was not continuous at the first point, but it is continuous at x equals 0. All right. For this next one, we're going to think a little bit about where it is continuous. So if I've got this piecewise function, based on past experience and what you know about graphing, you should be able to guess where it might not be continuous. Okay? And so the point we're interested at is the point 1, when x is 1. Excuse me. So here's my coordinate plane. And then, so the graph I'm supposed to use is x plus 1 for all the x values less than 1. So that's a line. It's got y-intercept 1 and slope 1. And it goes something like that. And then the parabola, the second part, it's, oops. The second part is just a parabola. It's upside down because the x squared is negative. And so really the only question I'm sort of asking myself here is when that parabola starts going, is it going to match up with this point? Or is it going to be one of the ones where they do like this and there's a jump? Well, the only good way to figure that out is to plug some numbers in. And if I'm going to do that, I might as well start going through my continuity checklist to be sure I don't do extra work. All right, so the first thing in our checklist is that we need to find the only place it might not be continuous is 1. So let's see what happens at 1. I need to find f of 1. And so the only place x is allowed to equal 1 is in the parabola part. So we're going to do 3 minus 1 squared, which is 2. Okay. Well, then we need to know about the limit as x approaches 1, f of x. So thinking back to section 1.4, the way we did these guys when we had to do a limit of a piecewise function was we did the two sides, sorry y'all, we did the two sides separately. So I'm going to need to do the limit as x approaches 1 from the left and the limit as x approaches 1 from the right before I can tell you what my final answer for the regular limit is. So if I'm doing 1 from the left, that means that I have to be looking at numbers that are smaller than 1. So I'm going to use the equation x plus 1. So that's just 1 plus 1, and that's 2. If I'm going to look at the limit as x approaches 1 from the right, then I'm going to use the other equation, the 3 minus x squared. And so that's 3 minus 1 squared. That's also 2. So since they're both the same number, they're both 2, then I can conclude that this limit that I originally was asking about is also 2. So there's the first two parts of my checklist. 1 checked and 2 checked. It existed. And then I ran out of room over there. But remember, the third part of our checklist was that the limit... Whoops, not 2. Equals the function value. And sure enough, they do. All right, so that means that this is continuous at 1, and the picture that I drew to start off with, because remember we were just asking where it might be, turns out that it actually connects up and makes its parabola shape going off that way. So that's all one big continuous function. And so starting to get into a little bit of the continuity on intervals, this thing absolutely is continuous at x equals 1. That's the place we were kind of worried that it might not be continuous. But it's also continuous everywhere else, if I think about what the graph looks like. And so it's okay to say that something is continuous everywhere, not just at a single point. And we'll talk in a little bit more detail about that in the second video. All right, that wraps up our first video. And so come back in the next one and we'll talk some more about this idea of continuous on intervals instead of points.